Welcome to The Explainer. Today we've got some incredible AI news that absolutely perfectly bridges cutting-edge artificial intelligence with life-saving infrastructure tech. I mean, if you've ever driven through a construction zone, feeling that sudden wave of anxiety as lanes abruptly shift and those concrete barriers just squeeze right in, you know exactly how chaotic these places can be. Well, engineers are finally using AI to solve one of the most stubborn, persistent mapping problems in these dynamic zones. We're going to break down a brand new learning framework called GAIA and see exactly how it ticks.
All right, let's dive right in. 898. Now that number represents the total fatalities in U.S. work zones in 2023 alone, and that's alongside more than 40,000 injuries. I wanted to start here just to instantly hook you into the real human cost of what we're talking about today. You see, accurate geometry perception, it isn't just a neat convenience for autonomous vehicles or smart traffic systems. It is an absolute non-negotiable safety requirement.
So, moving into Section 1, the deadly work zone problem. Let's look at exactly why mapping this edge of danger is so incredibly difficult.
Think about it. Work zones are arguably the most geometrically chaotic environments on our public roads. You've got lane narrowing, sudden lateral shifts, tapers, temporary barriers, and they all change daily, sometimes even hourly. So providing a constantly updated estimate of the actual drivable area is incredibly tough. Standard onboard cameras, they get blocked. LiDAR, way too expensive and requires dedicated gear. So, to understand the solution, we first need to look at how we currently try to track vehicles. Ultra-wideband, or UWB ranging. Basically, UWB is a low-cost radio technology. It uses precise time-of-flight measurements to provide distance estimation down to the centimeter. You slap UW tags on cars, put anchors on traffic cones along the perimeter, and boom, you get a structured network of distances to figure out the work zone boundary. But there is a massive catch here. UWB has a fatal flaw in the real world, NLOS, or non-line of sight noise. When UWB is deployed outdoors, the signals bounce off passing trucks, they get blocked by heavy machinery, and they suffer from multi-path reflections and sudden burst noise. These environmental interferences severely distort the raw distance readings. A system might actually think a car is 3 meters away from a cone when, terrifyingly, it's actually just 1 meter away.
And that brings us to the core issue. Clean numbers still produce broken maps. Up until now, engineers have treated this UWB noise simply as a signal processing problem. They used algorithms to try and clean up the raw distance accuracy in total isolation, completely ignoring the physical shape of the work zone itself. But here's the thing. If you have isolated errors on geometrically critical anchors, your reconstructed boundary will literally fracture. You can have totally clean individual data points, but when you piece them together, the map is completely broken.
That brings us to Section 2, Enter GAIA, Geometry-Aware AI. This is where researchers step in to finally fix this bottleneck.
This is a massive shift in thinking. Under the old paradigm, isolated signal cleaning, the only goal was getting the math right for a single anchor at a time. But the GAIA paradigm, which stands for Geometry-Aware Infrastructure Anchored Denoiser, forces the AI's denoising process to respect the actual physical layout of the work zone. It shifts the entire objective from pure signal cleaning to making sure the reconstructed boundary actually makes sense in the real physical world.
Moving on to Section 3, the 3 pillars of GAIA. Let's check out the core steps that make this possible.
So, the crucial takeaway here is how these 3 steps interact with each other. Step 1 is temporal range modeling. Since raw UWB signals have super high variance, GAIA tracks the measurements across consecutive time steps. This separates the short-lived noise spikes from persistent, real movement. Then, Step 2, latent anchor layout estimation. Instead of just predicting random coordinates, the AI actually learns a hidden topology of where those fixed traffic cones are likely located. It acts like a structural anchor. And finally, Step 3, deterministic distance projection. Once it identifies a consistent layout, it projects those denoised ranges onto a strict coordinate system. Basically, it penalizes any distances that violate the actual laws of physical space.
All right, Section 4, Inside the GAIA Architecture. Let's look under the hood.
The researchers published this detailed architecture in their paper, and honestly, it is a beautiful piece of engineering. Let's quickly walk through the 6 specific neural network modules that translate those raw, noisy pings into a highly accurate spatial layout. First up, the Pose MLP base module provides a frozen, pre-trained initialization just to keep things stable.
Next, the temporal refinement module uses a bidirectional GRU to capture forward and backward sequence dynamics. Then, the layout head steps in to infer the spatial geometry. Following that, a completely deterministic module called geodist computes the mathematically consistent distances. The prediction head then calculates any residual corrections. And finally, the gated fusion module elegantly balances the learned neural corrections with the strict geometry-derived distances to output the final squeaky clean data.
Now, I really want to highlight the layout head for a second, because it's kind of the secret sauce of GAIA. It bridges temporal signal processing with explicit spatial reasoning. Basically, when those raw UWB readings start drifting wildly, say because a massive semi-truck just blocked the signal, the layout head acts as an anchor. It pulls the AI's estimates right back toward a physically possible configuration. It's effectively asking the system, hey, does this corrected distance actually align with where we know the traffic cones are?
Section 5. The results. Fixing the broken map. Let's see if this geometry-first approach actually holds up in the real world.
So, the researchers tested GAIA on a real-world outdoor UWB dataset. They synchronized the UWB ranging with high-accuracy GNSS and IMU motion tracking just to ensure they had a flawless ground truth to compare against. And when comparing GAIA to POSE-MLP, which is the previous state-of-the-art, we see an 18.4% reduction in overall range mean squared error. That means the raw distance measurements got significantly cleaner. But that second bar, that other metric, is what really changes the game, a 15.5% improvement in polygon IOU.
That 15.5% polygon IOU metric is the real victory here. IOU stands for intersection over union, and it basically measures the spatial overlap between the AI's reconstructed work zone boundary and the actual physical layout. A 15.5% jump here proves that GAIA isn't just crunching and cleaning up numbers, it's successfully reconstructing the crucial drivable boundary. The map is officially no longer broken.
And finally, Section 6, the future of site safety. Let's zoom out a bit to wrap this up.
GAIA is an incredible breakthrough, no doubt, but it doesn't exist in a vacuum. It's part of a massive industry-wide shift right now, where robotics, AI, and wearables are completely redefining safety in high-risk environments. Think construction, oil and gas, or mining. We're talking about a whole new safety stack. You've got AI CCTV systems constantly monitoring for hazards, autonomous drones expanding the inspection area, and crucially, AI OT wearables. Just imagine a system like GAIA mapping the physical space, an AI camera detecting that a worker just stepped into a danger zone and instantly pinging that worker's smartwatch with a real-time haptic vibration alert to step back.
This closed-loop AI safety stack has a genuinely massive real-world impact. Under the old manual systems, identifying a hazard, logging it, and correcting the behavior could take anywhere from 24 to 48 hours. Today, with connected worker safety technology, that entire process, detecting the hazard, alerting the worker, correcting the action, and automatically logging the data, happens in under 5 minutes. 5 minutes!
The results are just so undeniable. For example, one deployment in Saudi Arabia saw a 63% reduction in on-site medical incidents. Because of results like that, industry standards are rapidly shifting. This technology is no longer just a nice-to-have competitive advantage for the early adopters. It's quickly becoming an expected minimum requirement demanded by regulators and major project owners globally. Basically, if you can monitor safety in real time, you're expected to do it.
Which brings us to a final thought-provoking question to end today's explainer. We started out by looking at the 898 lives lost in work zones in a single year. But with spatial mapping breakthroughs like GAIA perfectly reconstructing hazardous environments and wearable tech instantly alerting workers to danger, as AI becomes our permanent always-on safety supervisor, will work zone fatalities eventually reach absolute zero? It's a massive goal, for sure, but for the very first time, the technology is finally pointing us in that direction. Thanks so much for joining me to explore this explainer today, and keep your eyes peeled on how AI continues to reshape the physical world around us.